Okay, we can use Octave to actually plot the output y of t for that example problem we were looking at in the previous video. Here I've calculated, use Octave to express the Fourier series coefficients of the input. Here's my transfer function for that particular circuit. It was 1 over s plus 1. This Octave program script first calculates the input using the Fourier series coefficients we have for the input and plots that, and then calculates the Fourier series coefficients of the output. Notice here it's just the input coefficients times the transfer function at j and omega 0. In this particular case, omega 0 is 2 pi, and then I'm using the first 40 terms in the Fourier series expansion along with the DC term. So I've created a vector n here that goes from 0 to 40, and then use that to actually calculate both the input Fourier series coefficients and then also evaluate the frequency response at those harmonic frequencies. And then use fs exp to actually do that sum, that Fourier series sum, and come up with the input and output. And if we look at the corresponding graph, this is what the input function looks like. Again, this gives us some confidence that we actually calculated the Fourier series coefficients correctly for the input, because this matches the known waveform. And we see some ringing here, the Gibbs phenomenon at this discontinuity. And then here's the corresponding output function. This particular circuit can actually be viewed as a low-pass filter. So it's passing through the average or DC component, and it looks like maybe some of the first harmonic and second harmonic terms. A lot of the higher order frequencies have been filtered out by this first order low-pass filter. Of course, this particular system is a circuit, so we can also use LT spice to simulate the circuit and produce the output. It's a little tricky getting the input correct here. I used a behavioral source and just a periodic ramp function, and then took the exponential of that ramp voltage to get my exponential input. And then here's the circuit. I put an initial condition, an initial voltage on the capacitor, so that the initial transient won't appear. But if we run the simulation and then take a look at the output, and we see the input at the top, and then at the output at the bottom, and this agrees really well with our Octave results. So if I show the two, actually let me show them side by side. Try to scale them down a little bit so that the graphs are about the same size. You can see that we got very similar results from our Octave simulation to the LT spice simulation, giving us a lot of confidence that our calculations were correct, not only in calculating the input Fourier series coefficients, but then also in calculating the output Fourier series coefficients.